So in this example, I want to demonstrate something called the tabular method of integration by parts, which you will probably like. Notice here that we've got a power of x times an exponential, which is suggesting that you would want to use integration by parts. And usually you would let your u be the power of x, in this case the x cubed, and the dv the e to the 2x dx. And if you differentiate this, your du will be 3x squared. And that that expression will be involved in the next integral, the vdu. So your power of x would go down by 1, but you'd still have to do another integration by parts to get it down to x to the first power, and then eventually it would be gone. So this power of x is going to go down with each integration by parts. Well, you can shorthand this by thinking of your u as your differentiation column and your dv as your integration column. And we'll just make a table here. And what you do is you differentiate until your power goes down to 0. So derivative x cubed is 3x squared. Derivative 3x squared is 6x. Derivative 6x is 6. And derivative 6 is 0. So you keep differentiating until that column goes down to 0, and then you integrate on the right-hand side until you match the number of entries. So this will be e to the 2x instead of times 2, it's divide by 2, so 1/2 e to the 2x. If we integrate again, we'll get e to the 2x, and then we'll add another factor of 1/2, so this will be 1/4. And integrate again, we'll get e to the 2x. 1/4 times 1/2, 1/8. And integrate one more time, we'll get an e to the 2x, and 1/2, another factor of 1/2 times 1/8 is 1/16. And then there's an alternating sign pattern with the tabular method. You start with a plus, so plus, minus, plus, minus, plus. And the reason you do that is because the integration of parts formula, which is the integral of u dv is uv minus the integral of v du. And that's got that subtraction in there. And then if you do another integration by parts, that'll involve a subtraction. This subtraction will change it back to an addition or a positive. And that's why we got the alternating sign pattern. So then you just multiply on the diagonals and add those products up. And the 0 is not multiplied by anything here. So the answer here is going to be x cubed times 1/2 e to the 2x. So that'll be 1/2 x cubed e to the 2x. And then minus 3x squared times 1/4, so that'll be 3/4 x squared e to the 2x, and then plus 6x over 8, so 4 will cancel, let's see, 6/8, a 2 will cancel between the 8 and the 6 and give us 3/4, so that's going to be 3/4 x, so plus 3/4 x. E to the 2x. And then the last one, minus 6 over 16, which is 3/8 reduced, so minus 3/8 e to the 2x. And then plus c on the end. So we did all of our integration. We don't have to integrate one more time what's on the end, because we did that here when we integrated. So that's all there is to it. And your hint here is that even though this is easy to integrate, this involves multiple differentiations to get that power down to 1. If you start with a power of 1, it's going to go down to 0. So here, try this one real quick. Just another example. What if you wanted to do the integral of x to the 4th cosine x dx? That x to the 4th cosine is telling you you're going to have to do 4 integration by parts. But instead, try the tabular method. And why don't you try that right now and then check it against my, my work. So the part we're differentiating is the x to the 4th. So I differentiated until I got down to 0. The part we're integrating is the cosine. So I did antiderivatives over and over until I had enough to match up with my 0 term. So that would be 1, 2, 3, 4, 5 antiderivatives. And then we just multiplied on the diagonals, keeping the alternating sign pattern in there. So you should get x to the 4th sine x, 4x cubed cosine x, minus 12x squared sine x, minus 24x cosine x, plus 24 sine x, plus a constant. Did you get it right?